Hello, I welcome you all in this course on steam and gas power systems. Today, we will start discussions on impulse reaction steam turbines. So far, we have analyzed the impulse turbine. In impulse turbine, the steam slides over the blade surface, and due to change in the direction of the flow of the steam, the net force is exerted on the blade surface and power is developed. Now, in impulse reaction turbine, the pressure drop takes place in the blade passage as well. In impulse turbine, there is no pressure drop in the blade passage, but in impulse reaction turbine, there is a pressure drop in the blade passage as well. Due to this pressure drop, additional force is exerted on the blade. So, blade realizes two types of forces. One is due to change in momentum, impulse force, and another one by the reaction due to pressure drop in the passage. Now, if you look at the blade outlet angle of impulse turbine, so I will draw a larger figure. Blade outlet angle of impulse turbine this is the blade outlet angle B2, beta 2, and the passage, the opening perpendicular to the flow is this much. So, effectively we are using this much of space, and this is, suppose this is S, then this is S sine beta 2. This tip of the blade has some finite thickness. So, this is subtracted from here, multiplied by height of the blade, this is the length of the blade that is perpendicular to this board, number of blades multiplied by relative velocity at exit VR2 is equal to mass flow rate and specific volume at state 2. Now, from this equation we can simply find the value of sine beta 2, that is mv2 divided by length of the blade, number of the blades on the periphery, relative velocity at the exit, T will go on this side, and in order to find sine beta 2 we can divide this by 1 by S. This is for impulse turbine. But in reaction turbine, because there is a pressure drop, the VR2, this specific volume at exit increases, and at the same time relative velocity at the exit also increases. But the rise in relative velocity at the exit is more than the rise in the specific volume. So, that is why the beta 2 value in impulse reaction turbine is slightly less than this. But this equation has to be satisfied with the modified value of specific volume and the velocity, relative velocity. This equation has to be satisfied in any case. Now, in impulse reaction turbine, if we draw the velocity diagram for impulse reaction turbine. Now, for the inlet conditions, the diagram is going to remain same. Inlet condition, this is VR1, this is U, and this is V1, and this is blade inlet angle, and this is nozzle inlet angle, right. So, the steam is gliding over the surface in impulse reaction turbine, and same time the pressure drop is also taking place. So, without pressure drop, if you draw the velocity diagram, then it is going to be something. I will just extend this one. This is V1 and this is VR1. So, it is going to be something like this. This is beta 2, VR2, and this is V2, right. So, some impulse force is exerted on the blade, that is the net force due to this this component, this is the net force, parallel to this force is exerted on this blade. Now, expansion takes place during the flow in the passage, expansion of steam takes place. Due to this expansion, the relative velocity R2 increases, and increase is significant, and we get R2 up to here. This R2 is extended, and we get R2 here. This is actual VR2, right? And if we connect this with this one, we will get absolute velocity at exit. Now, in reaction turbine, because this is not in proportion, because in the reaction turbine, the VR2 is much greater than VR1. So, this has to be greater than this, just a minute, greater than this is VR2 and this is V2, right. Because VR2 is greater, because relative velocity at exit is also increased due to change in pressure during the course of flow of steam through the blade passage. Now, impulse force works in this direction, and reaction due to pressure drop works in this direction, right. And addition to this is impulse force, this is reaction force. Addition to this is the net force exerted on the blade, right. And if you want to have power developed in this type of turbine, then for developing the power, for calculating the power developed in this turbine, we will have to calculate the will component of the velocity, as we do in the case of impulse turbine. The will component of the velocity Vw is equal to V1 cos alpha 1 minus u plus V R2 cos beta 2. There are many ways of finding. If we have the value of alpha 1 and this beta 1 and this is alpha 2, then by many ways we can find the will component, if depending upon the information available with us. Suppose we have absolute velocity at inlet and outlet, then it is going to be V1 cos alpha 1 plus V2 cos alpha 2. If we have relative velocities at inlet and outlet, then VR1 cos alpha 1 and VR1 cos beta 1 plus VR2 cos beta 2, right. But normally it is taken like this, because in actual practice we know, in most of the cases we know the absolute velocity at inlet and nozzle inlet angle, that is measurable, I mean it is always available, and blade exit angle. That is why this expression is chosen to find the will component of the velocity, and power developed is Vw u divided by 1000 multiplied by the mass flow rate, right. The power developed formula is same, only will component in impulse reaction turbine changes due to pressure drop in the blade passage. Since the pressure drop is taking place during the flow inside a impulse reaction turbine, the specific volume of steam also increases. So, if you look at the arrangement of the blades in impulse reaction turbine on the rotor, there are moving blades, they are mounted on the rotor, the moving blades are mounted, and on stator the fixed blades are mounted. These blades remain stationary because they are mounted on the casing. Only these blades they rotate in a particular direction, and nozzles are fixed in these blades, fixed blades. In fact, they are fixed blade passages they are treated as nozzle, and together these fixed and moving blade row, they form one stage, and it is assumed that peripheral velocity remains constant during the single stage. But when there is a axial movement of the steam, and it is ensured while designing the turbine that velocity of flow or axial velocity remains constant. Since the specific volume of the steam is increasing while flowing along the axis of the turbine, the cross section area is increased in order to maintain constant velocity of flow. Now, because pressure drop is taking place in fixed blade and the moving blades, right, and the power developed, some of the power is lost in this turbine due to leakage, because there is always a gap between this here and here. So, this movement of steam does not participate in power development. So, this is a loss in the power, but it cannot be completely avoided, because we cannot seal both the sides, otherwise there will be no movement of the rotor. So, there is a term degree of reaction. Degree of reaction is enthalpy drop in rotating blades or enthalpy drop in the blades and total enthalpy drop in a stage. A stage means a stage consists of a row of fixed and the moving blades. So, we can always write the degree of reaction as delta H n plus delta H P, enthalpy drop in nozzles and enthalpy drop in blades. So, for a pure reaction turbine, the degree of reaction is 1, there is no enthalpy drop in the nozzles, right. But normally the turbines are impulse reaction turbine, because when there is a change in the direction of the motion of steam, it will exert force on the blades. So, the turbine is a impulse reaction turbine. Now, we will do elaborate analysis of degree of reaction. Now, degree of reaction is delta H B divided by delta H n plus delta H B. Now, efficiency of the nozzle is equal to V1 square minus phi V2 square by 2 delta H nozzles, right. Phi is the carryover coefficient. So, delta H n is equal to V1 square minus phi V2 square by 2 efficiency of the nozzle. Now, V2 square, this one is V2 square is VR2 square if we consider this triangle. If we consider this triangle, then it is VR2 square plus U square minus 2 U VR2 cos beta 2, right. And if we take V2 square, VR2 square common, then V2 square is equal to VR2 square 1 plus rho 2 square minus 2 rho 2 cos beta 2. Now, rho 2 is U by VR2. Now, from here, if we are putting this value here in this equation, we will get delta Hn or enthalpy drop in the nozzles is equal to V1 minus phi VR2 square, 1 plus rho 2 square. VR2 square 1 plus rho 2 square minus 2 rho cos beta 2. This is rho 2. This is rho 2. This is the enthalpy drop in the nozzle. Now, in impulse reaction turbine, it is assumed that this efficiency of the nozzle is equal to the efficiency of the blades. So, if we write expression for efficiency of the blades, that is going to be equal to VR2 square minus 5 VR1 square by 2 delta HB. So, enthalpy drop in the blade is VR2 square minus 5 VR1 square by 2 efficiency of the blades. Now, VR1 square, if we refer this triangle, then VR1 square is V1 square plus U square minus 2U V1 cos alpha 1. Right. Now, here if we take V1 square out, then it is 1 plus rho square minus 2 rho cos alpha 1. Now, putting this value here, VR1 here, we will get delta H B as VR2 square. So, this is V1 square. So, VR2 square minus 5 V1 square 1 plus rho square minus 2 rho cos alpha 1. Right. Now, we have enthalpy drop across the nozzles, enthalpy drop across the blades, and by putting this value together, we can find the degree of reaction of a turbine, impulse reaction turbine. Now, for impulse reaction turbine, there is a special type of turbine which is known as Parson's turbine. In Parson's turbine, the degree of reaction is half. When degree of reaction is half or 50%, then enthalpy drop in blades is equal to enthalpy drop in nozzles. Only in that case, the R is going to be half. Once degree of reaction is half, there is another characteristics of Parson's turbine is that blade inlet angle is equal to, nozzle inlet angle is equal to blade outlet angle, and nozzle outlet angle is equal to blade inlet angle, right. And now, based on the characteristics of Parson's turbine, we will solve one numerical on Parson's turbine, because in this lecture I was supposed to include impulse reaction turbine, degree of reaction we have already discussed. Now, generalized equations we have discussed for degree of reaction. Now, a numerical based on Parson's turbine. Now, in this numerical, the total tangential force on one ring of Parson's turbine is 1000 newtons. When blade speed is 100 meters per second, the mass flow rate is 8 kg per second. Blade speed means U, this U is 100 meters per second. The blade outlet angle is 20 degree. Determine the steam velocity at outlet from the blades. If the friction losses which would occur with pure impulse are 25% of the kinetic energy corresponding to the relative velocity at entry to each ring of the blades, and if expansion losses are 10% of the heat drop in the blades, determine the heat drop per stage and stage efficiency. So, heat drop per stage and gross stage efficiency has to be calculated. Now, gross stage efficiency is the work developed in the stage and the heat drop in the stage, that is the gross stage efficiency. If we refer this, so W is equal to VW and U, this is per kg kg per second flow of steam, the work is VWU, and VWU is V1 cos alpha 1 minus U plus VR2 cos beta 2. Now, V1 cos alpha 1 minus U plus VR2 cos beta 2. Now, if we multiply this by U, we will be getting the output, right. So, it is U multiplied by V1 cos alpha 1 minus u plus u v r2 cos beta 2, right. Further, W is equal to, so W is equal to, U is equal to rho V1, so it is going to be equal to V1 square, rho will go inside, rho cos alpha 1 minus rho square plus rho 2 square V R2 square cos beta 2, right. Now, this is the output and we have the enthalpy drop per stage and this will give the gross stage efficiency, that is output of the turbine divided by the enthalpy drop. Now, in Parson's turbine, because the things become simpler, because beta 1 is equal to alpha 2 and alpha 1 is equal to beta 2. Now, in this numerical, we will start with the force exerted on blades. Force exerted on blades is 1000 newtons, right, and U is equal to 100 meters per second, alpha 1 is equal to beta 2 is equal to 20 degree. It is given here, blade outlet angle. So, blade outlet angle automatically becomes this nozzle inlet angle for Parson's turbine. So, F force is VWU, because it is given in newtons, we will not divide it by 1000. So, force is 1000 newtons, sorry, this is work. So, force is MVW, right. VW is not with us. Mass flow rate is given here 8 kg per second. So, mass flow rate is 8 kg per second. So, force is 1000 newtons divided by 8 will give VW. So, VW here is 125 meters per second, this is 1000 by 8. Now, if you look at the velocity diagram for Parson's turbine, because these angles are equal, both sides of at the middle of the peripheral velocity vector, both sides are same, both sides are same. So, if we take this x and this is, suppose this is y, x is this much and this is y, right. So, x is VW by 2 minus U by 2 or VW minus U by 2. VW is 125 and U is 100 divided by 2 and it is going to be 12.5. So, x is 12.5, right, and y, okay, before we take y, we can take y as this x plus u, y is equal to, or y is equal to x plus u 10 alpha 1, because we have the value of alpha 1 only, we do not have value of beta 1. So, 10 alpha 1 is going to be equal to y divided by x plus u, right. So, y is equal to x plus u 10 alpha 1. If we take x plus u, then x is VW minus u by 2 plus u. So, x is, so this expression is VW plus u by 2 10 alpha 1 y. Now, y is equal to x plus u 10 alpha 1, x we have already calculated 12.5, u is 100, 10, 20, and this will give the value of y as 40.95 meters per second. Now, once we have the value of y and value of x, then tan beta 1 is equal to y by x or is equal to 40.95 divided by 12.5. From here we will get the value of beta 1, and the beta 1 is 73 degree. Okay. Now, with the help of these informations, we can find the value of VR1 also. VR1 is under root x square plus y square, and this under root x square plus y square is under root 12.5 square plus 40.95 square, and this is 42.8 meters per second. So, VR2 is 42.8 meters per second. Sorry, VR1 is 42.8 meters per second. Now, VR1 is with us. Now, in order to find V1 is 112.5. We have already calculated this length, 112.5 divided by cos alpha 1. Alpha 1 is cos 20. So, V1 also is determined from here, that is 119.7 meters per second. Now, pressure enthalpy drop in nozzle, that is isentropic enthalpy drop in the nozzles, and that is equal to enthalpy drop in the plates, because it is a Parson's reaction turbine. So, the enthalpy drop in a stage is equally divided between the enthalpy drop in nozzles and enthalpy drop in the blades, and that is equal to VR2 square minus phi VR1 square divided by 2 efficiency of the nozzle, right. And VR1 is given here, and VR2 is equal to V1, right. VR2 is equal to V1. So, enthalpy drop in nozzle is 119.7 square minus 0.75 multiplied by 42.8 VR1, yes, 42.8 square divided by 2 times efficiency of the nozzle, that is losses are 10%, so efficiency of the nozzle is 90% into 1000 to convert watts into the joules into the kilojoules, and this is 7.2 kilojoules per kg in the stage. Sorry, this is per is in the nozzles, and same enthalpy drop will take place in the blades as well. So, delta HB is also 7.2 kilojoules per kg. So, enthalpy drop per stage is twice of this. So, that is equal to 14.4 kilojoules per kg. Now, we have to find stage efficiency. So, stage efficiency is output divided by enthalpy drop. Now, stage efficiency is VWU divided by delta H in the stage. VW is will component, and U is the velocity, right. So, the will component is 125, right, and U is 100, right, and divided by enthalpy drop, that is 14.4. This enthalpy drop is in kilojoules and this is in joules. So, this has to be converted into the joules, and this will give us the gross stage efficiency as 0.868 or 86.8%. So, we have determined in this numerical, we have derived all the values which were required in this numerical, and that is all for today. In the next class, we will continue with the impulse reaction turbine. Thank you.